Okay, hey, Chapter 8, Earth Science, Chemistry. This is going to be exciting. I love chemistry. I love get to see what elements do. We're going to talk about that today. So our objectives that we're going to work on, we're going to state the distinguishing characteristics of an element, describe the basic structure of an atom, define atomic number and atomic mass, explain what an isotope is, and then we're going to compare solids, liquids, and gases. Pretty exciting. You should know quite a bit of this. So here we go. First of all, matter. Matter is anything that has mass, takes up space, and it's pretty much everything around you. It basically is anything that has space. Your desk, your book, a golf ball, everything. That's why everything matters. Everything's matter. And so, easy to define this one. Obviously, matter has different masses, so don't confuse mass with matter. Physical properties. Well, everything has a characteristic that we can observe without changing composition of that material. So, if I take a rock and I break the rock, it has a certain hardness to it. Water has a certain color, right? I mean, the sky. Now, that's the interesting thing about physical properties. Sometimes when we're trying to identify stuff, they're not very easy to use. So, for example, we look at color. We have the color blue. All right. Well, what is blue? What color is the sky? Is it baby blue? Is it light blue? Is it dark blue? Maybe the clouds are coming in. So you have to be able to quantify that instead of qualify, right? Quantitative, which means we have numbers associated. Qualitative, which means it is a feeling. Texture. Is it rough? Is it smooth? Is it in between? Right? So you could say on a scale of 1 to 5, it has a 5 for texture, with 5 being rough, 1 being smooth. Right? So you can tell what that is. And then we have density. Mass divided by volume. So we take the mass of an object, so we would weigh it, and then we would figure out its volume, whether we use the displacement method, or we could use graduated cylinders if it's a liquid. So density is a great characteristic, a physical property that we'll use to identify things. Chemical properties, basically, how do substances interact with each other to produce new kinds of matter? So, for example, oxygen and hydrogen interact, grab onto each other, and they produce water, a liquid from two gases. So, chemical properties. When you strike a match, that combustion is burning up. It's starting a reaction on that match head, and it's changing the materials into new kinds of matter. Smoke, ash versus sulfur and gunpowder. So, first thing that we need to talk about when we're talking about basically chemistry is the very simplest form in chemistry, which is an element. And if you look on your periodic table, I believe it's like on 143 or 144, periodic table, an element is the simplest form of a substance that cannot be broken down. So you've got hydrogen and carbon and nitrogen and boron and silicon and aluminum and gold and all these other things. And each one of them are a specific number of protons, neutrons, and electrons. And so they change a little bit. There are 92 naturally occurring elements. Actually, what's interesting is when I was a kid, the periodic table wasn't much bigger than 102, and now we've synthesized a large number of elements in the laboratory, and so now I think latest number was 118. Again, 92 naturally occurring, with the largest being silicon and oxygen. And if we think about what what silicon and oxygen are in, they're pretty much in most quite a bit of things. So an atom is the smallest unit of an element. So if we take one atom of an element, that's the smallest you can get of that substance that cannot be broken down. Now, that being said, that's where it has its chemical and physical properties. If we look at all of the crust, so we go back to, we talked about the inner and outer core, then we went to the mantle, and then we went to the crust. In all of the crust out there, 100%, pretty much 46% is oxygen, 28% is silicon. Now, it's combined with other things, and so it's in there. And then we have all these. But now, we just said there's 92 naturally occurring elements in the world. So basically, the rest of this entire pie is basically 90 elements. And aluminum being a great number, iron, etc. All right, so how does an electron work? What is it made up of? So we have little particles we call subatomic particles, right? Sub, small, atom, or beneath atom, right? So subatomic particles. So the electrons are on the outside, right? So the first shell can only hold 2, the rest can hold 8. I'll explain that down the road. All right, so electrons, it's a negative charge. I like to think of these things like people, right? And society. Negative people don't like to be on the inside, they like to be on the outside, and so they're negative, right? They're outside. So the electrons are on the outside in a place we call the electron cloud. All right, protons. Protons are the green ones here. They are positive. Man, you know, it's like positive people. They want to be on the inside. They want to be in the middle. All right, and then you got the neutrons. The neutrons actually have no charge. They are a neutral charge, but they like to stick next to the protons, right? So it's kind of like society again. You got neutral people who's like, yeah, what's up? How's it going? Yeah, everything's good. They like to be in the middle next to the protons. The positive people, so you got the protons and neutrons in the middle, the electrons on the outside. Again, positive charge for proton, negative charge for electron, neutral charge for neutron. Now, the nucleus is the center. It holds the protons and neutrons. Electron cloud, again, is that area around the outside that I talked about, where the electrons are held. And I've actually got a pretty good diagram right here of an electron cloud. Yeah, it kind of looks like a big fuzz ball. Well, that's because they're moving really, really fast, and we don't know exactly where they're at, but we do know that they're in their orbitals, right? And so we'll talk about that later. And if I look at this, I've got 2 protons and 2 neutrons. And so from that, I can tell you that this is a helium atom. Now, you're going, okay, how does he see that? Well, I'm gonna show you how to do this. It's a pretty neat trick. So in your periodic table, on page 142, 143, you'll see there's a chart. Go ahead and turn there now. Okay, so at the very top is a number. So we look at carbon. Carbon has the number 6 at the top. This is the atomic number. And when we look at that, again, this is a cheat sheet. So we look at that and we go, oh, the atomic number of carbon is 6. So that is the number of carbons, or number of protons in that atom. Pretty simple, pretty easy. So basically, it's a cheat sheet. If I look at vanadium, it has 23 protons. If I look at, I don't know, lead, it has 82 protons. If I look at gold, it has 79. If I look at hydrogen, it has 1. Our periodic table basically is a cheat sheet that allows us to classify the elements. And to be honest with you, there's so much information there, we use that quite readily. Mass number. The mass number is that number that has like 12.001. You know, it's the number at the very bottom that has multiple digits and a decimal point, right? And so basically, that number is the weight of protons and neutrons. Now, interestingly enough, I just said that the top number, like for carbon, which is 6, that's the number of protons. So I should be able to figure out quite easily the number of neutrons, which we can. And that's how I looked at that number. I said, oh, there's 2 protons, there's 2 neutrons. I looked at that and I go, oh, okay, that's helium. Well, basically what you do is you take the mass number. So in this case, in carbon, it was 12.001. Well, we round up or round down just using our regular 5 and up is round up, 4 and below is down. We round up, and in this case, we round down. So it's 12. 12 minus 6, 6 neutrons in that atom, right? So pretty easy to do. We look at, again, here's the atomic number. There's no atomic mass on this for some reason. Don't really know why, but you can see that all of those numbers, the atomic numbers, are listed, and we list them by the number of protons. So if you look at a trend in this periodic table, as we go to the right, the number of protons increase, and as we go down, the number of protons increase. Pretty good. Again, here's that 12.01. We round that down to 12. 12 minus 6, 6. That's the number of neutrons. So if we look here at a hydrogen atom, it has 1 proton, it has 1 electron. But if you look at our periodic table, it basically says 1.01 minus 1. So 1 minus 1 is 0. It doesn't have a neutron. So this one is unique in the sense that it doesn't have any neutrons. Again, if we look at chemical properties, the hydrogen and the oxygen and the hydrogen coming together, forming a bond, it changes from a gas, 2 gases, to a liquid. So what I want you to do is on page 144, it says the smallest particles. It's a little passage in your book. I'd like you to read that passage. Now, to read it, you have to go through the whole thing and take some time to look at it. And then once you've read it, you've learned basically that the word atom comes from the Greek word meaning indivisible. So here's your question. Is an atom really indivisible? And you need to explain your answer. If you do this in less than 3 sentences, you didn't get the job done. I'm just telling you. So again, read page 144. Answer this question right here. Okay? So what we know is that an atom has a nucleus, and in the nucleus there's a proton and a neutron. And we now know from research up at Fermilab, which is up in Chicago and some other places, that we can break that down into quarks and strings. Same with electrons. So if we look at the protons can be broken down into quarks, which actually can be broken down into strings. And string theory is a pretty cool cutting edge thing that's going on right now. And if you want to get into some of the coolest research on the planet, string theory is one of those things. So not always do we have a atom that has the same mass. So you can have what's called an isotope of an atom. Now, I'm going to make this as easy as it gets, and I think you'll understand it pretty well. All right, so you look at an element, and then all of a sudden you go, wait a minute. This element, so I'll give you an example. This element right here is a normal hydrogen, right? It has 1 proton, no neutrons, 1 electron. Okay? This one right here has a neutron. And what we know is that the mass of this atom actually is 2.01. Now, it's not written down here, but that's okay. How do I know it's 2.01 instead of 1.01? Well, we have an extra neutron, and that weighs 1. And so when I look at that, I go, oh, this is an extra heavy hydrogen atom, which is called deuterium, and this is radioactive, and so is tritium. All right, so this one, proton, 2 neutrons. Oh, now we have a hydrogen that weighs 3.01, notice the electron didn't change. The proton didn't change. The only thing that's changing is the mass number. So if you have a different mass number, you have a different number of neutrons. So for example, here's what we just looked at. This is a normal hydrogen, 1 proton. The electron's not shown. That's okay. 1 proton, but this one has 1 neutron. So this is H2, or 2.01 for a mass number. H3, 3.01, right? Helium. If we look at helium, you looked at me, or you looked at that electron cloud, and I said, oh, that's a helium. Well, if we look at our periodic table, helium has a mass number of 4, atomic number of 2. 4 minus 2, we have 2 neutrons, right? Here, we have only 1. So in this case, helium it would be helium-3, and so 3 minus 2 is 1 neutron. So this is an isotope that's in the negative, so it's 1 less. Same thing here, lithium. We have 3 neutrons, 3 protons. Here we have 3 protons, 4 neutrons. Okay? Pretty straightforward. Again, looking at the periodic table, atomic mass minus atomic number. Here's a good example too. Carbon 12 versus carbon 14. Again, 12 minus 6. The regular carbon atom being 6 neutrons. This carbon atom, which is an isotope, would have 8 neutrons. Here we go. Final stretch. Exciting. Solid, liquids, and gases. Solids. Everybody knows what a solid is. It's your desk. It's your book. It's the ceiling tiles. It's everything. And basically, it has a shape and it has a volume, right? So anything that has shape and volume, it's a solid. If they're really tightly packed, they can hurt as a solid, right? So obviously, you get hit in the head with the book. Don't know why you're getting hit in the head with a book, but if you get hit in the head with a book, it's solid, and its atoms are tightly packed, and you feel it with a bump on your head, and you're solid, right? And so when that happens, you get a bump on your head. Liquids. Liquid. Anything that has volume and takes the shape of its container. And so I got a glass of water. I pour the glass of water into a cup, right? Now it takes the shape of the cup versus the pitcher. I pour the glass of water on the ground. Now it lays out flat. And basically, because the atoms are less packed, they kind of move and roll all over each other, and they don't have that shape and volume, right? They have volume, but they don't have shape. And then gases. A lot of you know about gases. It doesn't have shape or volume. So when we pump up our tire in our car, we put the air hose on it, the tire then goes up. We're compressing air into that tire. And so you get like 32, 34 pounds per square inch, right? So that tells us how much gas is in there. While it has no shape or volume, it does have weight. How would we measure that? Well, what I would do is probably take a gas cylinder, one that you pump up your tire with, and weigh it empty, and then fill it full of air and weigh it again. And you'll find that there is weight there. This is just a diagram showing that, okay, the bonds are rigid versus in a liquid. The bonds are kind of flowing a little bit. In a gas, they're not really attached to anywhere. They're just floating around. And plasma we'll talk about in the sun, but we're not going to really talk about during this chapter. So let's go back to the beginning and just rehash what we learned today. So we learned today that we can distinguish characteristics of an element by looking at the periodic table. We can describe the structure of an atom. We can define atomic number and atomic mass. We can look at that. We can explain what an isotope is. And we can compare liquids, solids, and gases. Guys, did a great job today. Thanks so much. Real excited about chemistry, and you did a great job. Have a great day.